Hey, my dear students, welcome back. In this video we are going to talk about aldol condensation reactions that are important class of reactions in organic chemistry synthesis to synthesize big and complex molecules. So let's dive to the first case that you have. Let's start now with propanol. It is going to condensate with itself. So in basic condition, in the presence of ethanol is in equilibrium with enolate, because the OH from the base is going to form enolate by removing the hydrogen in the alpha position. And this enolate is going to react with propanol. Here you have the formation of one molecule of water. It's going to be used here. And this oxygen here is going to be protonated by one hydrogen in order to regenerate the base that we started at the beginning, because we mentioned here above that the base is in catalytical amount. So this carbon here that is in alpha position is going to attack this carbon here that serves as an electrophile to create a new carbon-carbon bond. What is going to be the product? Right, so you have the formation of a beta-hydroxy compound, beta-hydroxyaldehyde, because this is the carbon in alpha, this is carbon in beta, referring the aldehyde group. To finish the condensation process, you need to heat the solution to remove one molecule of water to finish the condensation process. Now what remains So what is this? In alpha, beta. So this is an enone, right? Double bond and the carbonyl group. This is the condensated product, final product, right? Okay, we are going to repeat this process multiple times, so you're going to remember it. Let's continue now to another case with ketones. Let's do condensation of this acetophenone. So the first stage is going to be the formation of enolate. Enolate is going to remove one hydrogen from here. This is going to be 2. And this bond is going to move here. So what you're going to have, right? And this is going to react with another molecule. Now, this is going to attack this one here, and another molecule of water is going to do the protonation of this here and to regenerate the base, because the base is in catalytical amount, right? So how you're going to make the connection of the new double bond, of the new carbon-carbon bond? Right? And the enone, that is the final step, minus one molecule of water, heat, it's going to be this compound. Right, this is going to be the final product of the carbonyl condensation. Let's move now to mixed aldol reaction condensation. One carbonyl partner must not contain alpha hydrogens and thus cannot form an enolate ion to become a donor, but does contain an unhindered carbonyl group and so is a good acceptor of the nucleophile. Those two that meet the following criteria is benzaldehyde and formaldehyde, right? Because they do not contain alpha hydrogens to enolate, even the formaldehyde does not contain. Let's take a look at an example. For example, this compound here that is a ketone reacting with formaldehyde. First stage is that this ketone is going to be converted into enolate. And after that is going to react with the formaldehyde. This is called a donor because this lone pair is used to form the new bonds, and this is called an acceptor that is going to accept this lone pair to form the new bonds. So in this case we use sodium ethoxide, and here the removal of hydrogen is done by the ethoxide, and this pair moves here, and now the ethanol, this formed here, is going to protonate the carbonyl group here, and this lone pair here is going to attack the carbon here that is electrophile. So you are going to regenerate the base and to yield the new product, that is this one. Right, and the final product, heat minus 1 molecule of water. So it's going to be an enon. Double bond is going to form here. Right, this is going to be the final product, plus the molecule of water. Let's move further. Let's move now in case of one carbonyl partner is much more acidic than the other, so it transforms into enolate preferably. So in this case, is this one that is going to transform easier to enolate because those two hydrogens, as we mentioned into alpha carbonyl substitution, are more acidic, right? And these are going to be converted far ahead compared to this one into enolate. So you're going to have enolate here. ET, I'm writing this because it's ethyl group, right? And it's going to react with this carbon here, right? And here, because we have sodium ethoxide, ethanol, one hydrogen is going to be used to protonate the oxygen here, right? So the final product is going to be what? So this is going to be connected to this carbon, and here we are going to have the formation of a tertiary alcohol, and again the remaining part. And when we do heat to do elimination of 1 molecule of water, the final product is going to be right? This is going to be the final product, plus 1 molecule of water. Now, third case, intramolecular aldol reaction condensation. You have to be careful here to the formation of multiple products. In this case, it's going to be formed a single product. So what is going to happen? First, it's 1,5-pentadiol. So what is going to happen? It is going to be the annulation of this hydrogen here, or this hydrogen here is the same. So now this is going to attack here because this made the annulation, as I mentioned previously. Here we have a molecule of water in this case. This is going to protonate this oxygen and to regenerate the base. And this now is going to attack here to this electrophilic carbon. How many members of the ring you have? 1, 2, 3, 4. So you have 4-membered ring. In this 4-membered ring, you have in one side, you have the aldehyde group untouched, and on the other side, in beta position, you have the formation of an alcohol. So alpha, beta, you have the formation of an alcohol. And if you heat the solution, you're going to have an alpha, beta. Let's move further. Here is the case that you can form multiple products. In this case, for example, the enolate can be formed here, here, or here, or here, because it's the same on this side. If you form it here, an enolate is going to attack to this carbon here to form 1, 2, 3 carbons cycle. That is so unstable and is not going to happen. If you do the annulation here, this is going to attack this carbon here. So it's going to form 1, 2, 3, 4, 5. So it's going to have 5 carbon the cycle. So in one position is going to be the carbonyl here untouched, and due to the fact that we did the alkylation here at this position, that is the beta position, alpha beta, is going to be formed the alcohol and the remaining carbons here untouched, right? And if you do the elimination, if you do the dehydration, you are going to have this final product, right? And on this carbon here we are going to do the annulation at this side, and it's going to attack here. What is going to happen? 1, 2, 3, 4, 5. Again, it's going to have the cycle 5 carbons, and we did annulation here and connect with this one here. What that means that this is going to be untouched. Let's assume that here, and this one is connected here, so is alpha beta is going to have an OH, and this remain untouched, so it's going to have a CH3 here. And during this bond formation with this one here, you have also a CH3 here. That is going to be here. And if you do heat dehydration, you're going to have this final product as a condensation, right? Okay, hope you understand up until now. Your brain, I know how it's working now. Okay, let's do more practice. Show the structures of the starting reagents. Here looks like we have a mixture. Now you have to count. You have to look at the carbonyl and count the carbons in alpha and beta. Alpha, beta. So at the beta here is going to be the break, because this is the alpha beta bond that is created, right? Between the carbonyl group that was here and the alpha enolate that was formed here. So the starting materials should have been a benzoaldehyde plus what remains acetophenone, right? So those two, how they are connected? They are connected in this way to give this product. Let's move further. Again, here you have to count alpha, beta. Here you are going to make the break in your mind. So what happened here? In one side here, you have the aldehyde because it does not have any branch. Even here it does not have any branch to be ketone. Here it was a ketone because you saw it and it has a branch here of CH3, this one here. So it's going to be an aldehyde in one side. And how many CH2? And after that comes this compound here. Looks like it's an intramolecular aldol condensation, in the sense that this here has attacked to this carbonyl group here, right? Let's move further. So here, again, you have to check alpha, beta, as a reference, this carbonyl group, right? What would have been the starting material? So 1, 2 carbons, here has been a carbonyl group. And on this side, 1, and this carbon here. So it's gonna be, right? This is going to be the starting material. and this has attack to this hydrogen here to make the cycle, right? Let's move to point D. How is done here? Alpha, beta, again. You immediately notice that the benzaldehyde and how it has happened? This has attacked to this one here, right? What about this one? This is phenyl. This is complex, really. It breaks here at beta, it breaks here at beta. So what is going to be? Phenyl, and after that, another carbon, and phenyl. Plus, what remains here? In both sides. So those two react in the same time to give this product, but this is more complex in terms of... Okay. That's it for this video. Hope you find it a little bit helpful. If yes, give a like and look forward to see you into the Kleisen condensation reactions. Up until there, peace.